Garrett here, a kernel developer at Red Hat, specialising in power management and firmware development. We are discussing today EFI and Linux. The future is here and it is awful. I have been told that his opinions on firmware quality are mostly unprintable, but I have seen some of them in print in the past. On behalf of Linux.conf.au 2012 in Ballarat, I hope we can all give you a very warm welcome. Matthew Garrett.
Hi. So, as he said, my name is Matthew Garrett. I work for Red Hat. I used to focus mostly on power management, suspend and resume on laptops, ACPI and stuff. More recently, I've been working on UEFI, which I'll introduce in a bit more detail. The main reason that I've ended up working on UEFI is that nobody else was. And I'm really, really bad at realizing that when there's nobody working on something, there's probably a reason for that. So, anyway, as you may have gathered from the talk presentation and my talk title in my introduction slides, I'm not necessarily a huge fan of certain aspects of UEFI, but we'll get to that. Firstly, we should talk about what EFI is. Now, you buy a PC at the moment, well, for the past 20 years, if you bought a PC, when you turn it on, it executes some code in ROM or in Flash that is called the BIOS, Basic Input-Output System. And the BIOS sits there, it's responsible for doing basic hardware initialization, and also provide some services to the operating system. There are BIOS calls you can make that then give you information about the hardware. BIOS is... Who has a phone? Right. The only person who's allowed to get away with that's Linus. So, the BIOS had been around for 20 years and hadn't changed a great deal. So obviously we've decided to replace it. Well, when I say we, some people decided to replace it with something completely new and different because everybody knows that the best way to make something better is to replace it with something new and different. It's a BSD licensed core, so in some ways this is actually an advantage over BIOS. You can go to a website, you can in fact go to SourceForge, and you can download the entire source code from Subversion for the core of pretty much every UEFI implementation. UEFI is a complicated piece of software, so pretty much everybody uses Intel's core implementation. And then you can build stuff on top of that. But it adds standardized support for new hardware features. There's a lot of additional functionality that you get through UEFI that currently you can't really manage using BIOS. It is... This time last year, I was a lot happier with life. Anyway, so this is an outline of EFI and the initialization process. This is just cut and paste out of the EFI specification, which you can download from the UEFI website at uefi.org. It's a mere 1,500 pages. Anyway, you have platform initialization. Now, platform initialization is actually interesting. The UEFI codes I mentioned earlier, the open BSD stuff, is the section to the right, starting where the dotted line starts. Platform initialization is actually a separate body of code called the pre-initialization environment. Now, that code is not public, that's hardware specific, and so that's stuff I'm not going to be talking about. It's effectively the really hardware dependent code. It's the stuff that has to program your memory controller, it's the stuff that has to do the power sequencing so you actually have voltage running to all your hardware devices. The PIE, the pre-initialization environment platform initialization environment rather, is actually not, it's defined by an EFI standard, but it is not part of the UEFI standard. So we can just ignore that. You bring up the hardware and then you initialize EFI, and you then have various EFI drivers. Now, one of the features of EFI is that previously when you wanted to write a hardware driver for the BIOS, you had to write it in x86 assembler, and you had to deal with the fact that you were in real mode, so you could only easily use memory below 1 megabyte, and it was kind of a pain to use even stuff above 640K. And you jump through hoops. You'd have to do things like attempt to initialize PCI devices despite the fact that your PCI device would be mapped somewhere just below 4 gigabytes, and you only have a 20-bit address register. EFI drivers are written in C. EFI is all running in either a 32-bit or a 64-bit protected mode environment. So from that point of view, it's a lot easier. Somebody has, in fact, even ported a POSIX C library to EFI. So in principle, you can implement as either an EFI driver or an EFI application Quake. Or actually, in fact, Emacs. For reasons unclear to me, nobody's done these things yet. So you load your drivers, that gives you access to your hardware. You are then able to, you also have a file system driver in EFI. This is another thing that distinguishes it from BIOS. EFI actually understands FAT. One of the other interesting things about this is that obviously, as some of us know, it is alleged that FAT is patent encumbered. The EFI specification provides a patent grant for the use of all FAT functionality, providing you're using it within the context of EFI. So we now actually have a completely justifiable reason to have the FAT driver in the kernel. You put your bootloader there, your EFI firmware is then able to directly execute that application. You don't need to do things like worry about embedding your bootloader into your MBR or your superblock of your file system. You don't need to have these block numbers. You can move the file around without everything going horribly wrong. You can upgrade it without everything going horribly wrong. It's kind of nice. So one of the EFI applications is typically your bootloader. There's in fact some work being done to turn Linux itself into an EFI application. So you'd be able to just run the kernel directly from EFI. You attempt to load an application, and then once you've got into your operating system, if your operating system started successfully, you initiate a handover between the operating system and EFI. Most of the EFI boot services, the functionality that was present in the EFI at boot time, is then discarded, and the operating system can use that memory. So despite the fact that EFI itself takes a lot of memory at startup time, you get almost all of it back. And then once you're into the operating system, it's an operating system. It's a PC. There are some calls to EFI that I'll get to shortly. So the boot services have a fairly rich set of interfaces, and then there are the runtime services that provide a more limited interaction between the operating system and the firmware. Boot services are things like memory allocation, the setup of timers, driver interaction, actually loading the files off disk, and so on. So they're pretty straightforward. If you want to write an EFI application or an EFI driver, then you just make this open protocol call. And every EFI protocol has its own globally unique identifier, or GUID. And you call open protocol, and if any devices in the system implement that protocol, you get back a pointer to a function table. To a table of function pointers. And then those function pointers you just call directly, and then magic happens. It's a lot easier than doing things with BIOS, where you need to manually load your registers and then make an int call. And that was kind of messy and unpleasant. So we can profit. It's great. Here's an example of an EFI protocol. This is the graphics output protocol, which is the EFI protocol that allows you to set a mode on the screen, get a pointer to the frame buffer, and then draw things. So you see we have this GUID. It's very catchy and memorable. And then you get back this pointer to a structure like this. So you have query mode, set mode, blit, and then a pointer to the currently set mode. If you want to ask what the current mode is, then you just call query modes with the appropriate arguments, and you get back another structure that gives you information about the mode. Set mode, you just pass in the mode that you want to set, and then it magically happens. The graphics driver knows how to program the hardware. You don't need to care about it. Blit, in principle, you can do blitting with EFI. This often isn't implemented, and it's also not particularly fast. Really straightforward. You can learn how to write an EFI application in almost no time at all. I did. I may have been drinking at the time, but anyway. Once you're into the operating system controlled code, so either your operating system specific bootloader or the kernel itself. As in, once you've finished pulling everything you need off disk, once you've finished doing all the graphics setup you needed to do, once you've finished grabbing files off the network, that kind of thing, once you no longer need to use the firmware's code to access the hardware, you call exit boot services. And at that point, the firmware stops using any of the boot services code. Boot services code and boot services data sit in regions of memory that are specifically flagged. So the operating system knows that after this point, it can use that memory itself. From then on, you can only use runtime services. And just to clarify, this confused me a little to begin with, but runtime services can also be called from within a boot services context. But once you've called exit boot services, you only have runtime services. The kernel then calls set virtual address map because runtime services work in a pretty similar way to boot services. You have a table and a bunch of function pointers, and you call those function pointers directly. There's no point where the firmware loads its own page tables, so the mapping between physical and virtual addresses in EFI calls must be the same as in the operating system. The firmware has all these pointers it's registered that point to various physical addresses. The firmware needs to know what the address map from the operating system looks like so that it can update all of those pointers. So you call set virtual address map having passed in a table of your physical addresses and the virtual mapping, and the firmware updates that. And from then on, the only thing you have to do is make sure that the runtime services code is executable, because you're executing this in the same context as the kernel. If you have hardware that supports non-executable memory, then unless you flag the EFI code as executable, then when you try to execute it, you'll take a fault for trying to execute non-executable code. It's not actually too bad. The EFI setup code in the kernel is only a couple of thousand lines. It's unfortunately a little tricky to read because the original implementation was cut and paste from the IA64 implementation. Probably the only significant kernel functionality that has been copied from IA64. So what runtime services do you get? Yes, a few. There's non-volatile variable storage, and this is actually probably the most useful bit of UEFI from our perspective. You have a region of flash that you can write variables to, and that's important for two reasons. The first is that you need to be able to tell the firmware where your bootloader is, and you need to tell it which arguments to pass to the bootloader. And that's put within a variable. It's a variable with a well-defined format and a specific name. You can actually have multiple boot entries, and then the firmware can show you a menu of which operating systems you have installed. This functionality is described in the specification, however, the way in which the UI is not described. So different systems have different UI for presenting those options. So we're still actually just using, rather than having a separate boot entry for every kernel, say, which we could do, we're just having one entry pointing at grub, and then we still use grub to choose between the kernels, because that way we know what the UI is going to look like. It's a lot easier to document. The other thing you can do with variables is store crash dumps. One of the biggest problems we had with BIOS and PCs previously was that you had basically 128 bytes of non-volatile storage, and most of that was being used by the BIOS, and if you wrote anything into it, your system stopped booting until you reset the CMOS. So that wasn't particularly useful. EFI, we have variables that are often up to 8 kilobytes big at the moment. Microsoft actually require that Windows 8 systems support 32 kilobyte variables. And we can just dump, if you oops or panic, we can just dump your D-message and the backtrace into a variable, and then you reboot, and the entire crash dump's there, even if the system locked up so hard you weren't able to get to the screen to read it. So that's the useful thing you can do with EFI. There's also time alarm configuration. EFI abstracts out the hardware clock so you can make an ACPI call. Wonderfully, ACPI 5 does the same in a slightly incompatible way. So we then need policy for whether we should use the ACPI interface or the EFI interface if both are present. One minor issue with this, the EFI specification specifies that the real-time clock must be in local time, not in UTC. However, it's not quite so bad because it also provides a time zone field, and it also provides a flag for whether or not the clock has already been updated for daylight savings. So if you dual boot, in principle, you can still handshake correctly and avoid any scenario where both systems change the time. So it's not ideal, but it could be worse. What's slightly weird is that this was the same for IA64, which was a processor that pretty much exclusively ended up running Unix.
Yeah.
So, also this was a specification written by Intel, not by Microsoft. Some things you just shouldn't ask. There's also a call that lets you reset or power off the system. There's an interface that lets you pass a firmware update to the system, and then when you reboot, the firmware will flash that. There's an interface for getting a monotonic counter, which is used for one of the mechanisms for updating authenticated or encrypted variables. They're not particularly interesting. You're probably never going to use them. The other thing that EFI introduces that makes the world better is the GPT, or GUID partition table. The old PC partition table, or the MBR partition table, was limited. First of all, if you assume 512 byte sectors, which pretty much everything does, then the maximum size disk you can express in MBR terms is 2.2 terabytes. You can only have 4 primary partitions. You can have a basically unlimited number of secondary partitions, but the firmware will typically only boot off primary partitions. And the only information you have about what a partition is, or what the partition's functionality is a single byte identifier. And despite there being 255 possibilities, there's overlaps there. I can't remember exactly which it is, but I think there's some wonderful thing where some OS2 identifier collides with some Solaris one. You can't uniquely identify whether a partition comes from a Solaris system or an OS2 system. You can uniquely identify that you probably don't want to care about the contents. But GPT fixes this for the most part. There's no practical restriction on partition size, given that it's a 64-bit value. There's no practical restrictions on the number of partitions, and you get a lot of metadata about the partition type. Not only does each partition type have its own GUID, you can also then add a freeform UTF-16. By the way, when I say UTF-16, at any point in EFI, I don't actually mean UTF-16, I mean UCS2. It claims to be UTF-16, but it doesn't support surrogate pairs, so you can actually only use characters from the basic multilingual plane. Anyway, so if you wanted to use Elvish in your partition labels, you're out of luck, I'm afraid. I think, actually, no, that's not entirely fair. I think Elvish wouldn't be a problem, but some of the other more niche Unicode character sets. So you get a lot of space for metadata. You can have partition labels that are Unicode strings. It's not so bad. Now, obviously, pretty much everything I've said up until this point appears to be in direct contradiction to the impression that I may have given you about the content of my talk previously. Thank you all for not leaving. There may, in fact, be some things I haven't told you yet. Like I said, Tiano Core is the Intel UEFI reference implementation. It's available for SourceForge. Intel take this, make some light modifications to produce the EFI development kit. We're now on to the EFI development kit 2. This is then in turn used by firmware vendors to produce their UEFI firmwares. Like I said, almost all of the code you can get from SourceForge then lands in your system firmware if it's an EFI system. It's made up of files. Like many things are made up of files. It is made up, in fact, of 7,061 files. To be fair, some of those are make files or readmes, but in any case, 7,061 files. Approximately 100 megabytes of code, which is approximately 10% of the size of the entire Linux kernel. Something I should probably mention at this point, EFI doesn't include, the Tiana core stuff is the hardware-independent code. It doesn't include many drivers. If we ignore the drivers from the kernel, we end up finding that Tiana core is actually larger than the kernel. Okay. So far, this is interesting. Our firmware is now kind of complicated. An EFI build may be several megabytes, which is larger than many kernels. Files contain code. I mean, that's pretty obvious, right? Where else are we going to put code? And what else are we going to put in files? Well, actually, there are many other things we can put in files, but they're not important right now. Code, as we all know, contains bugs. Always. So from this, we can conclude that UEFI contains bugs. This shouldn't surprise anyone, right? Other than the Linux kernel, which obviously contains no bugs at all, ever. Which is why our Bugzilla is completely empty at all times. Things contain bugs. UEFI contains quite a lot of bugs. So, like I mentioned, you call exit boot services, and all the boot services code has been discarded, right? Now, obviously, the firmware doesn't actually go out and overwrite that code. It just says, OK, I'm not going to make any more calls to boot services code. It's up to the firmware to then, sorry, it's up to the operating system to then actually do the clearing and then let the operating system use that. You have to call set virtual address map after exit boot services. If you call it before exit boot services, it returns an error that means call me after exit boot services. Read the documentation, you fool. That's not quite how it's written in the specification, but still. Anyway, since it has to be called after exit boot services, obviously it shouldn't be calling any boot services, right? Anyway, after spending a while trying to work out why a UEFI system I had was failing to boot, eventually resorting to a USB debug cable, which allows you to actually get debug messages out before you've got any graphics hardware available, I discovered that the reason that we were crashing on boot was that for some reason we were trying to execute some non-executable memory. This seemed a little bit odd. The reason we were trying to execute some non-executable memory was that we called exit boot services. We thought that this area of memory was just empty. And therefore, we'd flagged it as non-executable as a security feature. We then call set virtual address map, and the firmware jumped into some boot services code, which was non-executable, at which point we take a fault and die. This is actually fortunate, because we could instead have put some kernel code there, and then that would have been executable, and then maybe we just have executed arbitrary kernel code that might have done something like, I don't know, reformat your file system. So really, we got out of that. We were quite lucky there. We now have some fairly grotesque hacks in the kernel that map flag executable and prevent the kernel from writing boot services code and then hand it back to the kernel afterwards. That's probably the least favorite code I've ever written, ever. And I eventually reported this to Intel, and they said, oh yeah, that's actually a bug in the EDK code. It's fixed in EDK too. So you're going to be releasing firmware updates for every previous UEFI system, right? No, sorry, that's not really on the list of things that we're going to do. So that was cheering. Virtual memory, virtual addressing, wonderful, awesome, made so many things easier in software. It's the idea that you no longer have this direct one-to-one mapping between physical addresses and virtual addresses, and contiguous physical addresses are not necessarily contiguous virtual addresses. In Linux, anything that is higher than the top of physical RAM, when you map it into the virtual address space, will actually be mapped to somewhere in virtual address space, and you can't guarantee where. Now, obviously, because you can do this, and in fact, many popular operating systems do this, the firmware should know that this is going to happen, and the firmware should not make assumptions about things that are contiguous physical addresses being contiguous virtual addresses. Anyway, Apple have four regions in their EFI memory map that are physically contiguous locations that are marked as required mapping for runtime. So we have to map those into virtual address space so the firmware can access them when we make certain calls. And they all have contiguous physical addresses, but Linux mapped them as non-contiguous virtual addresses. So, yeah, I'll come back to that one actually. Here we have the contiguous physical regions, and then obviously you have non-contiguous virtual regions. All fine, all straightforward. No worries so far. If you take an address in the first block and add a constant offset, then if they're all contiguous, then the pointer will be pointing to a known location in another block. If they're non-contiguous, then it could be pointing to a gap between them. And so say you call set variable, and then the kernel loops because the kernel has just tried to access memory that doesn't exist. The kernel doesn't have a segfault handler, it just crashes. So if it's non-contiguous and if it just points to a hole, the kernel crashes. And that's irritating, that's a bug, and then you spend a while working around that by merging contiguous EFI memory regions that have the same flags into one EFI memory region. But like I said, you're not guaranteed to get this layout. You could instead get, say, this layout. So when we called set variable in order to tell the firmware where we'd put the bootloader, we wrote that into the middle of the system firmware and the system stopped booting. It's interesting that so many of the bugs we found have been in the variable code. There's one machine where we couldn't delete variables we'd set. So if you took the machine and you installed an operating system, that was fine. The operating system was installed and we set the boot variable. You then reboot, everything great. If you ever wanted to reinstall it, we'd format the drive and then attempt to set the boot variable again, and the write would fail. And that was a problem because the pointer to the bootloader included the GUID that uniquely describes the partition, which we've now deleted and recreated. So there was now a different GUID, which meant the existing variable no longer pointed at a real partition. It points us to a partition that no longer existed. So we'd fail to write that, you'd reboot, and your bootloader wouldn't run. Another system, coincidentally from the same vendor, reports the same variable multiple times. The way that you find out what variables are there is that you call getNextVariable, and you keep passing in the previous variable. You start off by passing in null, and then you get a variable back, and then you keep calling getNextVariable, passing the previous variable you got, and then you get another variable back. It gives us the same variable multiple times. That's not really in accordance with the specification. It's not actually even faintly in accordance with the specification. It is in fact a blatant violation of the specification. Didn't we already have the Nokia ringtone? Yes. Yeah, okay. Rebooting, it's easy, right? You may have read my previous articles on how rebooting PCs is actually amazingly difficult. But EFI makes this very easy because there is this call you make and you just say either I want to power the system off or I want to reboot. Various code then tries to access physical addresses directly. This works really, really badly if you still are running the operating system page tables because we're still assuming virtual addressing. And you reboot and the system oops it. Probably wasn't what you wanted. These are just some of the bugs we found in the runtime services. There are, I believe, 10 entry points into the runtime services. There are thousands of entry points into the boot services. The kernel only has to worry about the bugs in the runtime services. If you're ever writing a bootloader, you have to worry about the bugs in the boot services as well. Unfortunately, I'm currently working on making Grub work better with EFI. Really has me coming and going. So So there's a moral. There's always a moral. There's several morals. UEFI is poorly tested in the real world. If vendors have not tested their UEFI implementations particularly well with operating systems. In fact, several of these machines have bugs that are so bad that they won't install Windows via UEFI either. It indicates that nobody ever tested this code at all, ever. It contains a lot of code, and there are a bunch of bugs. Anyway, now, I was hoping this would be more of a surprise, but since Jonathan already mentioned it, people probably want to know something about UEFI secure boot. Secure boot, your firmware contains 3 types of key. One of them, PK, is the platform key. It's provided, well, the specification says this is under the control of the platform owner. It's since been clarified that by platform owner, they mean the person who made your hardware. Owner. There's only one PK on any system. There are then the KEK, the key exchange key. This is, you can have multiple KEKs on a system, and it's owned by the operating system or an operating system vendor. If you have a KEK, then you can add to the whitelist. In order to add to the KEK, you need to have an update that is signed with PK. So per specification, the only way at runtime you can add new keys to the KEK database is to have the update signed by PK, which means it needs to be signed by the people who made your computer. If you have a KEK, then you can push out updates to DB, and DB contains a list of keys and hashes that identify files that are permitted to boot. There's also DBX, which contains keys and hashes that are forbidden to boot. So even if you have an entry in DB, if you also have an entry in DBX, you won't be permitted to boot. So when you attempt to execute code, and this actually includes drivers, the firmware retrieves an encrypted hash from the binary. It checks to see what key that was signed with, and then it attempts to decrypt it with the public half of the key that's in either KEK or that's in DB. So it's signed with the private key, you decrypt it with the public key. You then have a hash. And you know that that hash was signed by somebody who had the private key. You then perform your own hash of the binary, get your own value, and if those two values match, then you know that the binary hasn't been modified, and you execute it. If either you don't have a public key for the signing key, or if the hashes don't match, then you refuse to execute it. So once you then have booted into your secure environment, you've had your secure bootloader and your secure kernel, you then check the firmware to work out whether you booted securely or not. And that means that you read back the secure boot variable. But get variable is a firmware provided service. Now remember I said the runtime services are there in a table of function pointers. That table is in memory. If you have executed malicious code, then the first thing that malicious code could do would be to point the get variable entry at its own code that returns the correct variable all the time except when you ask for secure boot, and then it can tell you that it booted securely even though you didn't. So for secure boot to work, you need everything from the hardware up to the operating system to be trusted. And that means you need every single piece of code that can modify hardware state to be trusted. So that's all the firmware code, that's all the bootloader code, and that's all the kernel code. Because if the kernel code is not trusted, you could boot a kernel, and then that kernel could set up a fake EFI environment, and then boot another operating system, and lie to it about the fact it's booted securely, and still steal all your encryption keys. Now, all kernel code. All kernel code. When I say all kernel code, that includes modules. In a secure boot environment, if you have a signed kernel that loads unsigned modules, your signed kernel is effectively a signed malware loader. And it's likely that that signed kernel will then be blacklisted. So we have certain practical issues with secure boot. We have no real mechanism at the moment for getting the keys. That's still something we're working on. those keys then need to be carried by the hardware vendors. That's something that needs to be negotiated. Who do you give the keys to? So if, say, Red Hat has a signing key, that's fine. Does Fedora also get to use the signing key? Well, maybe. Does someone who downloads Fedora, modifies it, and then redistributes their modified Fedora get to use the signing key? Well, okay, maybe. Except if we let people sign arbitrary code, then we're also letting them sign malware. And then the key gets blacklisted because it's used to sign malware. And there are still open questions about how well this interacts with the GPL, especially GPL v3, which is what Grub 2 is licensed under. Grub 2, of course, being owned by the Free Software Foundation. They may have opinions on this matter. And what happens to the out-of-tree driver vendors? You're no longer going to be able to build an out-of-tree module on your computer and then install it, because you'd need to have the signing key. And obviously you can't have the signing key on the computer, because then that could be used to sign malware and pushed into your system. So you would need to distribute signed drivers, but distributing signed drivers means distributing a driver that is signed that will load on every Linux version that you want to support. You will no longer be able to just rebuild a driver because your operating system, because your Linux vendor has released a security update that modifies the ABI slightly. Maybe that one's actually a benefit. So, I wrote the slides before giving the talk. It turns out that some of you still had your phones on, so maybe I was a little hasty. But it's okay, I'm sure you had good reasons for it. At this point, I would love to hear any questions you have. I can't promise answers, but we'll see where we go.
Doesn't Windows also have the problem with secure boot and drivers?
Right, so Windows doesn't actually have the problem with secure boot and drivers, because 64-bit Windows, since Vista, requires signed drivers. You can't load unsigned drivers on 64-bit Windows, and only 64-bit Windows is going to be supporting EFI. I suspect they'll actually extend this to 32-bit Windows if they end up pushing EFI on 32-bit netbooks as well. But yeah, Microsoft gets around this because they've already been requiring driver signing for the past 5 years. Coincidentally, the EFI signing mechanism is completely identical to the Windows driver signing mechanism, to the extent that all the structure members start with Win.
Hey, how does this interact with virtualization and booting operating systems inside of a virtual environment?
How does this interact with virtualization? And the answer is it doesn't. In a virtualized environment, you probably wouldn't bother implementing secure boot. You could do, and there's no reason why you couldn't. Your virtualization, your hypervisor could implement an EFI setup that does the secure boot restrictions as well. The signing keys, the public keys are inherently public. So there's no problem with getting Microsoft's public key and putting that into your virtualization environment. But right now, we're probably not going to see secure boot used a great deal in virtualization environments. Or, sorry, wait, was your question about virtualization and secure boot, or about virtualization and EFI in general?
Well, basically just, I guess, from the point of view of if I'm worried about all of this stuff preventing me from running things that I want to run, there's the part of me that thinks that I could possibly run a small hypervisor and then just run what I want to run in a virtual environment.
If you can get a signed hypervisor, then you can run under that. But the only way you're likely to be able to run a hypervisor on a system that will only boot Windows is by running the hypervisor under Windows.
Yeah.
So what can we do about this? I mean, it's absolutely untenable to have hardware that will not allow us to build our own drivers and such. And so is the only solution to build our own motherboards, or is there some way to kind of overwrite the nasty bits and allow our own software kernels and things to run?
So for x86, this actually isn't going to be as much of a problem as it could have been. After the backlash against secure boots, I managed to completely accidentally trigger last year. Microsoft actually have now changed their requirements. It is now required that any x86 systems allow you to disable secure boot. It's also required that any x86 systems allow you to add your own keys to the system. The reason we don't see this as a particularly useful solution, it's fine for enthusiasts. If you're happy going into your firmware and changing options, that's great. You'll be able to do this. But it doesn't, for instance, specify the formats that the keys have to be in for you to be able to add them. A vendor could require that they be in ROT13's base 64. The UI is not described. The naming of it's not described. You'll have to go into the firmware and then we'll be able to say, oh, if you want to run Linux, then you need to disable secure boot. To get into secure boot, you need to get into your firmware, which requires you to hit a key on your keyboard. We're not sure which. And then once you've done that and got into your firmware, you're then going to need to find a menu which might be called security, which might be called boot, which might be called advanced, which might be called beware of the leopard. And in there, you're going to have to find an option that's either called secure boot or permit untrusted binaries or Helen, for all we know. And it may be that you have to do this using the keyboard, or it might be that you have to do this using the mouse, and it could be that when you're doing this in a graphical environment, the menu options are being presented on rotating 3D spheres. It's not really very practical for us to document this as the best way to do things, but for most of us here, it's going to be okay. We'll be able to just turn this functionality off, and we'll be able to continue running Linux as we have done previously. For naive users, the days where you could say, here is an Ubuntu CD, here is a Fedora CD, please install it, that is going to be much harder. And right now, I really wish I had something really reassuring to say. At the moment, I don't.
But for example, I just changed the boot on a laptop for my son to multi-boot Fedora and Windows on the box.
Yeah.
Now, an article in lwn.net recently pointed out that Windows will not boot in that kind of...
Windows will still continue to boot in that scenario. Windows 8 does not require secure boot. The hardware certification program, which gets you the Windows sticker, which means that you get advertising free from Microsoft, and so you have a financial advantage. That requires that secure boot be on by default. If you turn it off, Windows 8 will still boot. You can still install Windows 8 on existing hardware that doesn't have secure boot. You'll still be able to dual boot Windows 8. So that's not the problem. The problem is really with the naive users. We're continuing to work on trying to actually find some sort of workable solution for everybody, but there's nothing I can tell you about at the moment.
You mentioned that there's a couple orders of magnitude more services available for bootloaders and things that run before the OS than OS services.
Yeah.
If we're running Linux as a bootloader, that would presumably mean we could take advantage of all of those services within Linux. Is there something awesome we can do with that?
You can take advantage of some of those things, but the problem is once the operating system's taking control, the expectation is that these won't be run. They're things that are going to make assumptions about hardware state. Once you've loaded the native graphics driver, it would be a really bad idea to try to use the EFI one. Like, a really bad idea. And the same with the disk controller, if you try to use an EFI call to read something. But once you've called it, in theory, in Linux, we could never call exit boot services. And then you could continue using the EFI drivers forever. But there's not really much of an advantage to do that. The EFI drivers are always going to be slower than the native Linux ones.
So a couple of things. One is that the reasoning behind this is around, continuing to lock down platforms and providing assurance to media companies and all sorts of crap, right? But so while you may still be able to load in 5 years' time Windows in a non-secure boot environment, will it still allow you to go to Hulu and load videos or not? And I realise that's philosophical rather than purely technical.
One thing that I want to make absolutely clear here is that secure boot is not an effective DRM mechanism, because you cannot guarantee that the firmware is telling you the truth. It is not TPM based. There's no hardware protections that allows you to be sure that you have booted securely. Like I said, malware could lie to you. It can tell you that you've booted securely when you haven't. So it is vitally, vitally important that we do not let anyone get the idea that secure boot is a DRM mechanism. Because if anybody starts believing that's true, then people start using the DMCA against anybody working against secure boot. Anytime anybody says this is a DRM mechanism, you need to say it's not. Completely, full stop, never. There is a step beyond this. There is an ongoing specification growth for TPM-based EFI trusted booting. Right now, that's not looking like it's going to happen in the consumer space simply because a TPM costs too much money. There's so many laptops sold without TPM hardware. And requiring a TPM would raise the price of laptops by a measurable amount.
You were talking before about how you've been working with Intel, submitting bug fixes, and they've said, oh yes, we have more bugs than we know what to do with. Are you seeing bugs coming back from, or bug reports coming back from other vendors? And I guess in general, how open is that process?
We don't have any access to vendor bug trackers for the most part. So there's the UEFI forum runs plug fests. Previously it's been twice a year. This year it's looking like there's going to be at least 3, maybe 4. But these are places where all UEFI members can turn up with hardware and operating systems and validate interoperability. And that's pretty much the environment where we try to work out whether we're doing anything wrong, and then when you have people you can talk to there, you can work out why this is failing and try to come up with an answer. We've been, when I say we, I'm now talking about Red Hat, we've been getting more aggressively involved in working with the UEFI people on this. We became full UEFI members last year, and we're now, the next Plug Fest is in February, we'll probably be at that. That gives us an opportunity to find some of these bugs. It gives us an opportunity to have an open discussion. However, getting in there is limited to EFI members, and it's not as open as we would like it to be when working with the Linux community. In fact, anything that occurs within the UEFI discussion meetings, we're not allowed to talk about publicly up until the point where it is already public. So the development model is quite alien to those of us used to open source development.
Yep. So if secure boot isn't for DRM, what is it for?
Microsoft do actually have a legitimate point here. We're seeing an increasing number of people. Windows has got more secure recently. I said that and nobody laughed. That's amazing. But it's actually true. Windows has got more secure lately. Anything that does attack the operating system, Microsoft have got much more proactive at pushing out updated scanners that will tell you about that. So if you now attack the operating system itself, it's easy enough to find you there. And in Windows 8, they're actually adding additional validation functionality. So the bootloader, the firmware will only load the bootloader if the bootloader is signed. The bootloader can then verify the kernel to make sure the kernel hasn't been tampered with and boot that. The kernel can check that all the drivers it's going to run haven't been tampered with and run those. So you have a chain up to the point where you start running user space where you can be fairly sure that nothing's been tampered with. And that means you know that when you run your virus scanner, the answers your virus scanner gets back from the kernel have also not been tampered with. People are now starting to get around that by attacking the bootloader. So on BIOS systems or on EFI without secure boot, you tamper with the bootloader, you have the bootloader load the kernel and then modify the kernel in memory. And then you patch yourself into the file system driver. So there's this file that contains your malware, and any normal application that tries to read that, including virus checkers, gets told there's no such file. Secure boot protects against that. At least secure boot protects against that, assuming there are no bugs in UEFI. I'll leave the rest as an exercise for the listener.
You mentioned that in passing, one of the things was using, I think it was runtime services to update firmware. Does that have any chance of being usable from Linux to actually let vendors not make you boot into some weird old operating system to update your firmware?
Yes, it does. In fact, it works in pretty much the same way that the Dell firmware updates already work in Linux. You load a file into memory, you pass a pointer to that memory to the firmware, and then it sets a flag, you reboot, and then the firmware flashes that image. Downside of secure boot is that it requires that all BIOS updates themselves be signed in order to prevent you just replacing the firmware with one that doesn't do secure boot. So you're no longer going to be able to do local BIOS modifications unless you actually attach a flash program into your system. But it is going to make BIOS updates a lot easier than it did previously.
Now, you say there is this repository of rejected keys. So the expectation is that if an operating system gets compromised, for example, its key becomes blacklisted. How long before Windows random vendor drivers all over the place eventually get used as an attack vector? And will they actually blacklist Microsoft keys? The whole cathedral crumbles down the minute you start attacking that way. So,
yeah, that's a question you'd have to ask Microsoft, and I recommend that you do ask Microsoft because we've asked Microsoft and they won't tell us. We don't know what Microsoft's blacklisting policy is going to be. We don't know if so for instance, were there to be a flaw in Microsoft's bootloader on the pressed Windows 8 DVDs, we don't know if they would blacklist that key or not. They should do, but if they did, then that would render every single Windows 8 DVD useless. It's a completely open question at the moment.
I'm interested, what is your favorite whiskey?
I'm just going to go with pretty much anything that comes in a glass bottle rather than a plastic one. Anyway, so I think that's a great question to end on. I'm afraid we're out of time and people should go and have lunch. I'm here all week. Feel free to grab me if you have any further questions. And thanks for being a wonderful audience.
You don't get to go so quickly. Obviously a very popular and controversial subject, and we really, really do appreciate the work that you've done, and we really appreciate the talk that you've presented. So on behalf of Linux Conference Australia 2012, we give you a glass penguin with gold plating from Ballarat Gold and a little card. Thank you very much.
Appreciate it.
Very much so.
Thank you.